right, let's get right into it. For decades, the story of the incretin hormone GIP, or glucose-dependent insulinotropic polypeptide, seemed pretty simple. But in just the last few years, that whole story has been flipped on its head, creating what is, without a doubt, one of the most fascinating physiological paradoxes in modern medicine.
And this slide right here is the paradox in a nutshell. We now have two completely different types of drugs for obesity. One class activates the GIP receptor, the other one blocks it. And yet, when you combine either of them with a GLP-1 receptor agonist, both approaches result in profound and frankly remarkably similar weight loss. So, how can activating and blocking the very same receptor possibly produce the same powerful outcome?
So, to really get to the bottom of this, here's how we're going to break it down. We'll start with the classic view of GIP as an obesity hormone. Then we'll look at the clashing clinical evidence for both agonism and antagonism. And finally, we'll dive deep into the cellular mechanisms that might, just might, solve this entire puzzle.
So let's just state the central question one more time, because it's so critical. How do these opposing molecular actions converge on such a similar and potent therapeutic effect?
To really appreciate just how strange this situation is, we have to go back to the established dogma, the idea that GIP is, fundamentally, a key driver of weight gain.
For the longest time, our view of GIP was that it's this key anabolic hormone. It's secreted by your gut, especially after a fatty meal, and its main job is to promote efficient nutrient absorption and storage. I mean, it even earned the nickname the obesity hormone.
And when you look at its actions throughout the body, that view makes perfect sense. It promotes lipid storage in fat tissue, it messes with insulin and glucagon in the pancreas, and it even helps you absorb more nutrients in the gut. I mean, the picture was crystal clear. GIP is all about efficient energy storage. And the real smoking gun, the piece of evidence that cemented this whole idea, came from preclinical studies. You take a mouse, you knock out its GIP receptor, and it just doesn't get fat, even if you feed it a horrible, high-fat diet. For years, this was the definitive proof that blocking the GIP receptor was the logical way to treat obesity.
And then, the first major plot twist arrived. A brand new class of drugs came along that didn't block the GIP receptor, they activated it. And the results? Well, they were absolutely stunning.
Tirzepatide, this dual GIP and GLP-1 receptor agonist, just blew everything up. It turned out to be even more effective for weight loss than the GLP-1 agonists we already knew were incredibly powerful. This flew directly in the face of the idea that activating GIP was obesogenic. Something very different was clearly happening here.
And the case for agonism just got stronger and stronger. The next-generation drugs, like retatrutide, a triple agonist that also hits the GIP receptor, started showing weight loss of up to 24% in trials. You know, that's getting into the same territory as bariatric surgery. The evidence was just undeniable. GIP receptor agonism was a huge part of this powerful new wave of weight loss therapy.
But just when the field was busy rewriting the textbooks to fit in GIP agonism, the story took another, even wilder turn. That original idea, blocking the GIP receptor, was finally put to the test in a big way. And guess what? It also worked.
This is really crucial. Recent phase 2 data for Maridebart cafraglutide, which is a GIP receptor antagonist plus a GLP-1 agonist, showed a mean weight loss of over 16% at 52 weeks. These numbers are right in the same ballpark as the dual agonists. It's incredible. And if you look closer at the data, you can really see just how potent this effect is. In people with obesity, the weight loss was massive and dose-dependent compared to placebo. Same story for patients with both obesity and type 2 diabetes. So it turns out the original hypothesis was also correct. And what's more, the case for antagonism gets a huge boost from human genetics. It turns out that people who are just born with certain genetic variants of the GIP receptor that don't work as well, they consistently have a lower BMI. This isn't a mouse model, right? This is a lifelong natural experiment in people that points directly to the idea that having less GIP signaling promotes leanness. Okay, so we've got two completely opposite pharmacological strategies. Both are backed by solid data, and both lead to the same result. The only way to figure this out is to go deeper, right down to the cellular and receptor level. So, let's look at the three leading hypotheses trying to explain this.
This really is the multi-billion-dollar question that labs all over the world are racing to answer. The convergence point is obvious. Doing something to GIP signaling is the key, but the how is still a massive puzzle. So here are the top 3 contenders. First, there's functional antagonism. The idea here is that hitting the receptor with an agonist over and over just causes it to desensitize and shut down, which basically mimics a blockade. Second, receptor populations. Maybe agonists and antagonists are working their magic in different places, like the brain versus our fat tissue. And third, and this is where things get really interesting, is biased agonism.
This image does a great job of visualizing what we mean by biased agonism. See that green line? That's tirzepatide. When it binds to the GIP receptor, it doesn't just flip a simple on-off switch. It preferentially fires up certain downstream signals, like CAMP, while being much weaker at activating others, like IP1, especially when you compare it to the body's own GIP. And this could be the whole secret right here. Tirzepatide might be biased towards that beneficial GAS-CAMP pathway, which we know helps with insulin secretion. At the same time, it sort of avoids the other pathways, like GAQ/IP3, that might be more involved in GIP's obesogenic effects, like storing fat. So in a way, it's a smart drug that cherry-picks the good signals and leaves the bad ones behind. And that could explain everything about why this agonist has such powerful anti-obesity effects.
So where does all this leave us? Well, while the exact cellular mechanism is still a hot topic of debate and investigation, the clinical path forward is actually becoming incredibly clear. Just look at this timeline. It shows a truly stunning acceleration. It took us decades to go from discovering a GIP antagonist fragment to developing GLP-1 agonists, but in just the last few years, we've had the approval of a dual GIP agonist and now incredible phase 2 data for a GIP antagonist. The pace of innovation right now is just extraordinary. So the ultimate takeaway is this: whether you stimulate it in a very specific, biased way or you block it entirely, manipulating the GIP system alongside GLP-1 activation is, right now, the most powerful pharmacological strategy we have for treating obesity and improving metabolic health. The paradox might exist in the lab, but the clinical benefit is absolutely undeniable.
And that really leaves us with a final, and I think crucial question for the future of our field. As these multi-hormone therapies keep pushing the boundaries of what we thought was possible, achieving results that we once only saw with surgery, are we actually witnessing the end of an era for single-target therapies in metabolic disease?